Okay, so probability. What do you guys, what's your definition of probability? Like, what do you think it means? What's probability? Right, the chance of something good.
Chance of something occurring?
Yeah, chance of something occurring, right? So I usually define it like this: probability of E, and I use the letter E for an event. Okay, so basically I make a fraction to kind of think about how it can occur. So the way I look at this is the number of ways, and that's not hashtag, I'm old, we call that number, okay?
So
Not countable. Number of ways an event can occur over the number of all possible outcomes. Okay, because you have to have it something to compare it to. So if you're looking for, what's the chance that it can happen, or you have to have a comparison, right? So this right here, if you list this out, we say all possible outcomes, and we'll look at some examples. It's called the sample space. So what you'll do is a lot of times we'll just list the sample space. Okay? So for an example, if we have a die, so we'll just call this example one. Best way I know to do this is just dive in and start looking at these problems. So what's the probability with one die, and it's 6-sided, this isn't Dungeons and Dragons or whatever y'all play with a 20-sided dice. I don't know. Who knows what I'm talking about, right? Okay. The fantasy world, we don't have that. It's 6-sided dice. So we have one. What's the probability of rolling a 3 or a 5? Okay. So, okay, I think we can probably do this off the top of our head, but let's just think about it. So first of all, the first thing I like to be able to do is think about the sample space. All right, so for a die, what are the outcomes? Again, it's a fair die. So what could it land on? A 6-sided die. 1, 2,
3, 4, 5, and 6.
All right. So that is the total of everything that could happen, right? So the size of that, or the number of those, are always going to be your denominator. So now I know that my denominator is all the possibilities, which in this case, or the number of all possibilities, which in this case, there's 6 possibilities. Okay. What's the matter?
Die is technically
Die is singular. One die. Dice is plural. We're only rolling one die, because if it's a pair of dice, then it's a different sample space. Okay? Yeah, it's only one die. Learn something new every day. All right. So now, then you look and say, well, how can I roll a 3 or a 5? So how many ways can that event, the specific event, is rolling a 3 or a 5? So how many of those are there? 2. There you go. Now you won't leave it as 2 over 6. You'll make it 1 over 3. Okay? So 1 out of 3 chance to roll a 3 or a 5. Okay. Now, question. What is the highest answer you could ever get in a probability, and what's the lowest answer? So whatever our range of answers. So anytime we're doing probabilities, when we're doing probability of an event, it has to be less than or equal to this number and greater than or equal to this number. What is the highest answer you could ever get, and what's the lowest answer? Yep. That's exactly right. Just think about rain chances, right? The chance of rain. It's not, nobody's going to say there's 110% chance of rain tomorrow or today, right? So 100% as a fraction is 1. You just be 1 over 1. All right, and then the smallest you could ever get is 0, because we could say, we could make up something silly. What's the probability of rolling an 8? There is no 8. So it's 0/6, all right? What's the probability of rolling a 1, 2, 3, 4, 5, or 6? There's your 6/6, which is 1. Okay, so you could ask that question. That's the boundary. Okay, so if I said the probability of something occurring was 1.7, what would you say to that? Is that possible? Can it be bigger than 1? No, not possible. But if I said the probability of some event was 0.25, is it possible to be 0.25? Yeah, that's like a fourth. Right? So, all right, that's okay. All right. So just want to kind of get that out of the way to make sure we know what our boundaries are when we're working these problems. Okay. So we could ask all kinds of questions with a die. Okay. Now, so I like to do different scenarios and see if you can write the sample space out. So we'll come back to a pair of dice in a little bit, because that one is usually what I play games with. Like, anybody ever played backgammon? Yay, good, backgammon, that's a math game, right? But you roll 2 dice, or a pair of dice. Monopoly is 2 dice, right? If you played it, you know, all right. So let's go to a different problem. So just remember this. How many ways can that certain event occur, and how many total outcomes are there? This is what we'll always do to get our probability, okay? So I'm gonna leave that there, that little definition, and we'll do another problem. Okay, here's what I want you to think about. So, we'll call this one example 2, flipping 2 coins. You're gonna flip 2 coins or the same coin 2 times in a row, however you wanna look at it. First, I wanna know, what is the sample space? So what are all the scenarios that can happen? So I want you to list out, you have 2 coins, and you're gonna, you know, so you can think of it like this. I'm taking 2 coins and flipping them at the same time. What are all the scenarios that can happen? I want you to list them, okay? List. And then I want to know, what's the probability that both coins land on heads? So probability that both land on heads. What's the probability that there's exactly 1 coin is heads? Okay. So first, let's list the sample space, and let's double check and see if you're right. Okay, anybody want to take a stab at the sample space? Leah, what do you think all the scenarios are for flipping 2 coins?
Okay, so there's head and head.
Okay. So, I just list them like this, just like you said, I do HH, so that could happen. What else could happen?
Tail and tail.
Tail and tail. What else could happen?
There's head and tail.
Yeah.
And then this is where I started to wonder if.
Well, just think, the first one's a quarter and the second one's a nickel.
Okay.
So the quarter could land on heads and the nickel land on tails, or the quarter could land on tails and the nickel land on heads. If you think of it like that, then you have to separate those two. But if you think of it as 2 separate coins, this is everything that could happen. First coin is head, second coin is head. First coin is tail, second coin is tail. First one head, second tail, first one tail, second head, and that's it. That's all the scenarios. So the sample space is how large? How many things are in the sample space? 4. So you know Once we go to start doing those probabilities for the two coins, the denominator should be 4. Now see if you can answer B and C. Everybody good with this? How we got all 4 of these? Okay, I mean, is there any other scenario you can think of? Don't say it can land on its side.
I was gonna ask,
No. It cannot land on its side.
anything's possible. It could happen.
We're
Could
just not
land
good.
on like a piece of gum and then a piece of wood on its side.
I can get a coin to land directly on its side. I get extra credit. How about that?
Sure, plus 100, minus 100, we'll give you extra credit.
Sounds like a plan.
All right, so what's the probability that both are heads? So how many ways are there to land both heads out of that? One. Out of all is 4. 1/4. Exactly one coin is heads. So 2 out of how many? 4, which will then reduce to 1/2. Very good. Okay. Very good. Any questions about that? So I'm trying to do like the famous problems first, like there's the die problem, there's the coins problem. Now let's do a pair of dice. Okay, we might as well go ahead and bite the bullet and do the sample space one time for a pair of dice because we'll need it. Okay, so it sounds like, well, why is that a big deal? Well, you'll see. So we'll call this one example 3. So for a pair of 6-sided dice, let's do the sample space. Well, the markers are crazy. Example 3. A pair of 6-sided dice are rolled. Part A. List the sample space. I'm going to need a lot of room. So let's do a little bit of it together. It might help if you think there's a red die and a green die. Just like because Leah was kind of contemplating, is that different? And it is. So just on a die, you could have this. Look real quick, guys. I want to show you that this is different. A 1-6 and a 6-1 can both occur. There's 2 ways to roll a 7. Or those are 2 of the ways to roll a 7. Like a sum of 7, right? The first die could be, like this could be the red die and that could be the green die. 1 and 6, or the red die could be a 6 and the green die. Here's what I usually do. I start like this. The first die is going to be a 1. What could happen with the second die? It could be 1, it could be 2, it could be 1 and 3, 1 and 4, 1 and 5, 1 and 6. All right? Now, the first die is always a 2. List everything. The first die is always a 3. The first die is always a 4. The first die is always a 5. The first die is always a 6. Now, you list the sample space. But it's good to do it one time and have it because you'll refer to this on certain problems. It just takes it. It's just tedious, but it's good if you write it out. All right. So I'll just catch up to you. This is what your paper should look like, right? So 2-1, 2-2, 2-3, 2-4, 2-5, 2-6, so on. And I do it like this on purpose because I'll show you it's going to be easier to get some your sums when you're working these problems. All right. Arm's tired. What is that called?
Sample
The
space.
sample space. How many of them are there? How many scenarios?
36.
36, that's exactly right. There are 36 different possibilities and all that. I could have used fundamental counting principle to get the size of sample space, because look, now we go back to the last lesson, right? You've got a die and a die. How many possibilities for the first die?
6.
Times, how many possibilities for the second die? 36 is the sample space, okay? So notice the double sixes, which you love in backgammon, only a 1 out of 36 to get it. Snake eyes, 1 out of 36. But typically, we're asked to find sums. So like, what's the probability of getting a sum of 7, okay? So now, we have to narrow in on that. We know what are all the possible outcomes. We know all the possible outcomes, so that's our denominator. And you gotta go through and figure out where all the sum of 7s are and add them up, okay? So look through your sample space and see how many times the sum of 7 occurs, and that's your numerator. And I'll show you in a second a really easy way to find it. So in each column, should there be a sum of 7? Yeah. Okay, so notice you just eyes go to this diagonal here. This is the highest probability situation where a pair of dice is rolling the sum of 7. You got a 1, 6, a 2, 5, so 1, 2, 3, 4, 5, 6, 6 out of 36. So the diagonals usually are the sums that you're looking for. Okay, so you would reduce that fraction to what? 1/6. Probability of a sum of 3 or a sum of 4. So could you add up all the probabilities of sums of 3 or sum of 4? What's that? How much? Yeah, 5 out of 36. Everybody say it's these. 1, 2, 2, 1 is a sum of 3. 1, 3, 2, 2, 3, 1 is a sum of 4. So it's 5 out of 36. So it's more likely to roll a sum of 7 than it is to roll a sum of 3 or a sum of 4. There's more 7. All right. And we could ask all kinds of things. Okay. All right. Any questions about that? Okay. Everybody has your sample space there. All right. What's next? What's the more famous? Another famous probability. We did coins and we've done dice. What's another famous thing that you do probability with? Wait on that one. That'll be my 4th one. You're right. We're going to do marbles in a second. Before we do marbles, there's one more. My favorite.
Counting cards. Decks of cards.
Cards. Okay? Cards. Deck of cards. Okay? That's dollar bills. That's not dollars. All right. So, oops. Well, we'll erase that. I think by now we know what we're doing. So now, let's go to example 4, a standard deck of cards. Now, I'm not going to write all this out. The sample space. I'm just not, because why? Why do I not want to write it out? 52 cards in a deck. Very good. So let's take some notes. There's 52 cards in a deck. How many suits are there?
4.
4 suits. So you have, out of this, you have what? We have 13 what? Clubs, 13 diamonds, 13 hearts, 13 spades. All right, so there's that. Because remember, it's 2 through 10, Jack, Queen, King, Ace. Okay? And ace is not a face card, by the way. Doesn't have a face on it. All right. So now I can ask you some probability questions. So probability so if you're just drawing a card, so we're gonna, so if we're drawing a card at random, here's some probability questions. Part A, what's the probability of drawing a diamond? Part B, what's the probability of drawing a 7? Part C, what's the probability of drawing a face card? Part D, what's the probability of drawing a heart or an ace? All right, so see if you can answer each of those. And try to reduce your fractions. Okay, so let's look at some of these. All right, Maria, probability of getting a diamond. How many diamonds are there in a deck of cards? 13. 13 over 52, well, that ends up reducing to what? Well, think, look, a 52 is 4 13s. So 52 is 4 13s, that's 1/4, right? We could cancel, all right? Probability of a 7. Anybody want to give that one? All right, Hank.
113.
Right, you got 1/13, which is right, because it's 4 out of 52, because there's 4 sevens. And that's 1/13. Okay, very good. Probability of a face card. How many face cards are there in a deck of cards? There's not 52 face cards. Yes. So it's okay. Let's think. So just think about the clubs. You got ace of clubs, 2 of clubs, 3 of clubs. None of those are face cards. Dot, 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 all the way to 10 of clubs.
What is face card?
Got a face on it. Jack, queen, king. So there's 3 face clubs per suit, because there's a jack, a queen, and a king. Okay? No, that's why we're talking about it now. Okay? So each suit has 3 face cards. 3 jack, queen, king, jack, queen, king, jack, queen, king, jack, queen. Say it 3 times fast, right? So how many, if there's 3, there's 12. That's exactly right. 12 out of 52, which is how much? Does that reduce at all?
3 out of 13.
3 out of 13. Okay, very good. All right, last one, be careful. This one can be tricky. So anytime there's an or like this, when there's 2 scenarios, or 2 things included in the scenario, you gotta be careful about double counting. So we have a way to avoid that. Okay? So, anybody want to give us their answer for the probability of drawing a heart or an ace?
Four 13.
All right, you got 4/13.
Got 16 over 52, which.
All right, let's see, 16 out of 52, which you said is 4/13. So let's think about that. How many hearts are there?
13.
How many aces are there?
Subtracting the part.
Yes, so you're right. So I've already counted over here the ace of hearts. I can't count it again. So there's 3 other aces other than that one. So it is 16 out of 52. You can't say, well, there's 4 aces, well, you already counted one. So the way we do this, typically, if we have the probability of A or B occurring, we can also do it like this, the probability of A plus the probability of B minus the probability that A and B both occur. So this is a little formula you can do when you have OR, okay? You can find each separate one and then subtract if it occurs the same. So for instance, on this, you could either just mentally know that don't count that heart twice, that ace of hearts twice, or you could do it like this. Probability of a heart or an ace, right? So hearts is how many out of 52? 13. Aces is how many out of 52? Just all the aces. 4 out of 52, right? But minus, is there a way to get a heart and an ace? Yes. The ace of hearts. And how many of those are there? 1. So that's 1 out of 52. So 13 plus 4 minus 1 gives you 16 out of 52. Or you can just mentally know to not count that one twice. Basically, what's happening here is one card is counted twice. So we subtract that one card off. Or you just mentally know to not count it twice and make it 16 out of 52. All right. Any other thing we can think of with this? So that's we're just doing basic probabilities, okay? So how many ways can something occur over all the possible outcomes? All right, now, I want to change gears a little bit, and then the last group that we'll look at are the marble question. So, this type of question, a lot of times, students that kind of don't see how to get both the parts of that probability. I'll call this one example 5. I call this the true-false test. Okay. All right, you got a true-false test, and let's say a student has a 5-question. There's we'll say there's a 5-question true-false test. What is the probability of getting a 100? Okay, very simple. So I'll show you how we do it. So now on this one, I've got to get my sample space. I got to know how many possible outcomes are there on a true-false test, right? What are the total ways I could answer it, right? So I would just put my 5 blanks here. So this is where I would use fundamental counting principle. When it gets to these, like there's a true-false test or a multiple choice test, I would do this. First thing I'm going to ask myself is how many total scenarios are there? So how many choices do I have for the first question? How many choices for the second question? Third, fourth, fifth. And fundamental counting principle says to multiply. So if you multiply all those, that's going to tell you how many different ways there are to answer the test. So when you do all this and you multiply, there's how many different ways? So if there's 32 total different ways to answer it, that's the what? Is that the event, or is that the sample space? That's the sample space. Because that's all the different ways. Like, what does this mean? I could do true, false, true, false, true. That's one way. True, 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 true. False, false. It'd take forever to list them out, right? It'd be a pain. So I'm not going to do that. There's 32 ways. Now, out of all of those, if it's a 100, how many of those are right? 1. There you go. So the probability of getting a 100 on a 5-question test is only one way out of 32. You got to know the sample space. 1 out of 32. Does that make sense why it's 1? Does that help? Yeah. Okay. Sorry, wish I'd known this was. So next time you take the ACT, at least you. All right. So so what would be different if I had a 4-question multiple choice? You wouldn't put 2, 2, 2, 2. You would put. I'm sorry. If I had 4 responses multiple choice, it wouldn't be 2. It would be 4, 4, 4. However many you have. Okay. Let's do the marble problem, because what I want to talk about is, like, what if we have two things in a row that happen, right? So, or different situations. So let's say we have red, white, and blue marbles, okay? So we have, example 6. You have a jar, there's 6 red marbles, 8 blue marbles, and 4 white marbles. First question. Okay, what's the probability of drawing a blue marble? Part B, what's the probability of drawing a red marble given you already drew a blue marble? I know it's wordy. And then I'll do if we try to draw 2 in a row. Okay. On this, is it easy to see the sample space?
Yes.
How many are in the sample space? 18 marbles, right? So on the first question, it's pretty standard. You're just gonna ask yourself, how many blue marbles are there out of how many total? Bless you. So that's pretty standard. So what's the answer to the first one? Just don't reduce it, just give us the, well, how many blue marbles are there? There's 8 blue.
I read red.
That's okay. 8 out of 18, so you could take what could we take out of that? 2, leaves you 4 out of 9. Okay, so we probably should get in the habit of reducing. Now, what is this telling you here on the second one? You're gonna draw a red marble, but you already have drawn a blue marble. So that means what's happened now to the jar? 1 less marble. So now there's only 17, that's exactly right. So what this does is, this right here changes the SS. What's the SS? Sample space. It changed the sample space. So now, there's still how many red marbles?
No.
6, but it's not gonna be 6 out of 18, it's gonna be 6 out of 17. So basically what we're saying is your odds go up of getting a red if you've already drawn a blue one. Now, there's 2 other scenarios that could happen here. What's the probability of drawing a blue and then a blue with replacement? Okay, so let me explain to you how this works. You're gonna have 2 problems together. So basically what we're looking to get is the probability of a blue and then a probability of a blue. And when you do 2 events like this, that one then the other, you multiply your probabilities. Okay, and that'll give you the final probability. Okay, so when you're basically gonna draw 2 marbles out of the jar, but when it says with replacement, I take the blue out, I put the blue back in, then shake it up and draw another marble. So the first time drawing the blue out, what's the probability? 8, I don't know why I keep picking blue, sorry. 8 out of 18, which is 4 out of 9. Then if you're gonna do it again, you're gonna multiply your answers, okay? You're gonna multiply your probabilities. So now, I've put the blue back in, I've shaken the jar up, now what's the probability of getting a blue again? So, again, make sure you understand what this means. With replacement means you take the marble, you put it back, you replace it, you put it back in.
Is that another phone?
Okay, so it's the exact same answer, 8 out of 18, which is 4/9, and then you just multiply. So it's 16 out of 81. So because it's tougher to do the same thing twice, that's why it becomes a smaller probability. Okay, so when you do an event like this, and then do it again, you would, now, the next one. One last question. What's the probability of me getting a white and a white without replacement? Okay, so now, without replacement. So when I go to do this, it's probability of getting a white times the probability of getting a white a second time. So let's just do one at a time. What's the probability of drawing a white marble the first time? 4 out of 18. But now what this means is without replacement. So now when you go to do the second one, you haven't put that marble back in. So now, what basically is happening, it's 6, 8, and not 4, it's 3. There you go. Right? So there's still 6 red, there's still 8 blue, but now there's only 3 white. So now what would that be? 3 over 17. And then you would multiply, and that's how you get your answer. So notice if it says without replacement, I gotta change the problem because now there's one less white marble and one less total. So to change that. And then when you're doing 2 events in a row, you multiply. Is that okay? Does it make sense? That's really it. Okay. The last thing I can think of is the only last type of problem is maybe like if it's conditioned. Let's say we're doing students in the school, freshmen, but we'll do this will be the last problem. Freshmen, sophomores, juniors, seniors, girls, boys, so I'm trying not to use the same letter. Let's say we have a table. These are your students in high school, right? This is freshman, sophomore, junior, senior. So let's say we got 20, 30, 15, 10, 25, 40, 20, 20. Okay. So let's just say that's the table of students at school, because we know we have hardly any students here. Most everybody's at home. So let's just say this is the problem here. So this is a type where we're going to find maybe a probability, but we don't use maybe the whole entire sample space. Maybe the question is like this. So we'll call this one example 7. So what's the probability that of a student being a sophomore given they are a girl? So once I put this given they are a girl, that changes the sample space. Now you're only looking at the total number of girls in the school. So if we looked at this, how many total girls are there in the school? Total. 75. So now that's your sample space, only the total number of girls. So now you have to see how many sophomore girls are there out of the girls. So what would you say out of that? 30 out of 75. Okay. So that's the last one I can think, but I think it's pretty simple. Okay. You could also say, what's the probability of being a girl given they are juniors? You're basically trying to see what percentage of juniors are girls. So what would that be? No, 15 out of 75.
15 out of 35.
Juniors now is the sample space. There's only 35. See? So 15 out of 35. Had I said, what's the probability of being junior given you that they're a girl, then it would have been different. Then it would have been 15 out of 75. See how that's different? That's basically
basically it. Okay, I'm gonna stop this.
Okay, that ends the lesson for now.